Good day all, this is Professor Friday coming at you one more time. What we have on the docket for today is a little bit of work with parametric equations. We've been given parametric equations and asked to find what is dy dx, as well as the second derivative d squared y dx squared, and then compute for what values of t is the curve concave upward. So, the given parametric curve is going to be x equals e to the t, y equals t times e to the d, t times e to the negative t. There we go. So first thing I'd like to point out is, and this is just good old-fashioned practice right here, I might even recommend doing this if there wasn't a very particular part of the question. I'm going to say let's eliminate the parameter. Now, I would like to point out this step is for funsies because the problem does say for what values of t is the curve concave upward. That means we want our final answer in terms of t rather than just in terms of x's and y's. So, the part that's for funsies is to eliminate the parameter. We just said that x is equal to e to the t power. If we apply a natural log to both sides, that tells us that the natural log is equal to t. Now, the reason that's important to us is because y is equal to t times e to the negative t, which is a fancy way of saying t over e to the t power. Negative exponent forces the e to the t down into the denominator. Now t we just said was equal to the natural log of x, so my new numerator is the natural log of x. My old denominator was e to the t. We just established that e to the t was equal to x, so if you wanted a slightly more simplistic form of this, we could use y is equal to the natural log of x divided by x. Again, this step was for funsies because we enjoy doing it. Now back to the task at hand though, let's recopy down what we have. X is equal to e to the t, y is equal to t times e to the negative t. Now the formulas that we have for the first and second derivative. Anytime we differentiate anything in terms of parametric equations, we're going to interpret this as the derivative with respect to x of whatever we have. So for the first derivative, dy dx is equal to the derivative with respect to x of y. This is the rate of change of y with respect to t divided by the rate of change of x with respect to t. Now that means we have a couple of derivatives to take. X is equal to e to the t. I like to joke around with my classes about this one. Alright, so what's the derivative of e to the t? They all say e to the t, and I say, yeah, what's the derivative of that? And we have a good laugh about it. Now for our other one, y is equal to t times e to the negative t. This one's going to require a little bit more work due to the fact that t times e to the negative t is a product of two things. So we're going to do first times derivative of the second plus the second times the derivative of the first. Now, for first times derivative of the second, the extra negative sign comes from the negative exponent on the t and the chain rule. So put it together, we got ourselves negative t e to the negative t plus e to the negative t. I'm also going to do one quick step of algebra here, and we're going to call this e to the negative t times 1 minus t. We'll just go ahead and factor out that e to the negative t. E to the negative t becomes 1. Minus t, e to the negative t becomes minus t. The reason that we do that will become apparent momentarily. Now, let's keep this going. So moving on to our second page, we just said dy dx is equal to dy dt over dx dt. We now have expressions for both of those things. Dy dt, let's go ahead and grab this expression back here. This was e to the negative t times 1 minus t all over dx dt we just said is equal to e to the t. Now if we wanted to, we're going to have to differentiate this again, but we could do a little bit of algebra to make this a little bit nicer for us to work with. That is, we're going to take the e to the negative t divided by e to the t, subtract those exponents, and now we have e to the negative 2t. This will make our derivative a little bit easier. I'd like you to recall with me what I just said about taking derivatives in terms of parametric coordinates. If we also want a concavity, d squared y dx squared, this is like saying take the derivative with respect to x of the original dy dx. Now with that in mind, we also said anytime we take a derivative with respect to x, that's like saying take the derivative of the inside thing with respect to t and divide it by dx dt. Well, our inside thing this time is dy dx. So we're going to differentiate the first derivative with respect to t and divide that by dx dt. Now thankfully we have a slightly more basic form of dy dx. We still need to differentiate this with respect to t though. So we'll say derivative with respect to t of e to the negative 2t times 1 minus t all over derivative of x with respect to t, which we still have on camera up here. That's still going to be e to the t. Alright, move down to the next line. So now we want the derivative of e to the negative 2t times 1 minus t with respect to t. Once again, this is a product of two things, so we will do first times the derivative of the second plus the second times the derivative of the first. We're going to need some chain rule for this. That'll be negative 2 e to the negative 2t. This is still all over e to the t. Do a little bit more algebra. This is negative e to the negative 2t. Let's see, we'll distribute that through. Minus 2 e to the negative 2t plus 2t e to the negative 2t all over e to the t. That's just using the distributive property up here. Now we'll combine some like terms. I see that my first two terms here are like terms, so we'll combine them. Call that negative 3 e to the negative 2t plus 2t e to the negative 2t all over e to the t. A little bit more algebra to do. We have a common factor up top of e to the negative 2t. We'll still have negative 3 plus 2t. In the denominator, we'll still have e to the t. Now, just like we did for the first derivative, we recognize that e to the negative 2t divided by e to the t, I can subtract those two exponents. So by subtracting those two exponents, I'll get e to the negative 3t times negative 3 plus 2t. That is my final answer for the second derivative of y with respect to x. Now that almost completely answers our original question. I'm going to scroll back up here for a second so that we can reread our original question. It says, find the first derivative of y with respect to x and the second derivative of y with respect to x. We have officially found, let's see, oh, no, not that one. Hang on, there we go. Yeah, that one. The first derivative as well as the second derivative. Let's see if we can get both of those on the screen at the same time. Oh yeah, we can. Alright, now, the supplemental extra part to this question did say for what values of t is the curve concave up? For what values of t is the curve concave upward? Now, let's flip this guy over. We'll need this. We'll also need the second derivative. The reason that we'll need the second derivative is because concavity is determined by the second derivative. Now, the definition of concave upward, well, I guess it's not necessarily the definition, but the way that we calculate concavity is whether the second derivative is positive or negative. For us, we want the second derivative to be positive because that's what defines concave upward. So, I'm going to grab my expression for the second derivative from up here. E to the negative 3t times negative 3 plus 2t is greater than 0. If we solve this inequality for t, we're going to have ourselves an answer. Now, something that I'd like to point out is we have an exponential times something linear. Exponential, and this bad boy is linear. Now, an exponential function like e raised to a power is guaranteed to be greater than 0, or guaranteed to be positive. So, given that it's guaranteed to be positive, we pretty much just need to worry about whether this linear factor is positive or negative. Now, in order to multiply something positive by something else and get a positive result, that means that this linear term needs to be greater than 0. That way, if we say take something that's guaranteed positive times something that can be positive, the result will be positive. So we take our linear term, or linear factor, set it greater than 0. We're going to solve this for t. Solving this for t is an exercise in algebra. We should be super good at it by now. I'm getting a final answer for this one of t is greater than 3/2. So to recap, this is the interval for t on which our curve is concave upward. Interval of concave upwardness. Yeah. Alright. Well, that concludes this tutorial. I hope you found this helpful and useful, and I'll get this posted as quick as I can.